an AI-generated post for your viewing pleasure. Unlocking few-shot learning, the power of Siamese Transformer Networks. Imagine being able to recognize a new image with just a single glance. Your brain does this effortlessly. But can AI rise to the challenge? A cutting-edge study reveals a game-changing way to combine fundamental design strategies, significantly boosting machine learning's ability to classify images with minimal examples. Welcome to the groundbreaking world of Siamese Transformer Networks, where the future of AI hangs in the balance. Before we dive in, let me just say that the implications of this research go far beyond simple image recognition. We're uncovering the potential for a multidimensional approach that can transform numerous fields of AI as we know it. So let's get into the meat of the paper and see how this all unfolds. In the ever-evolving tech landscape, few concepts have garnered as much intrigue as few-shot learning. Imagine if a machine could learn to recognize a completely new object after seeing it just once or a handful of times. It's a feat that mirrors human capability, where a single glance can sometimes suffice to identify something new. Researchers are now tapping into this fascinating idea, and today we're highlighting a recent paper that proposes an innovative architecture designed to make few-shot learning more efficient and effective than ever before. The Siamese Transformer Network. This study integrates two core methodologies, the global and local feature extraction strategies. By harnessing the strengths of both, the authors have developed a network that not only improves classification accuracy, but also simplifies the learning process. The implications of this research are substantial, particularly as we look to apply these findings to various domains, including autonomous driving, healthcare monitoring, and even robotics. So grab a seat, and let's take a closer look at the intricacies of this exciting work. To kick things off, let's define a couple of essential terms. At the heart of this research is few-shot learning, AFSL, a subfield of machine learning focused on training models to understand new concepts with minimal training examples. This contrasts against traditional models that require vast datasets, making FSL particularly attractive for real-world applications where data may be scarce. Another key term is metric learning, which involves teaching a model how to measure the similarity or distance between different data points in order to classify them accurately. In the context of this paper, the authors utilize the Vision Transformer, VIT, a cutting-edge architecture that processes images as collections of patches, rather than relying on conventional convolutional networks. By employing a Siamese architecture, the study's framework integrates global features representing an overall context of images, with local features that focus on specific regions. Now that we've set the stage, let's dive into the technical contributions that make this work so compelling. Next, we'll explore the technical contributions of the Siamese Transformer Network in detail. I'll break down the innovative aspects of their approach and unpack how the authors went about integrating global and local features to improve few-shot learning. The Siamese Transformer Network, SAIN, redefines the way we conceptualize image classification by integrating two critical components in its architecture. It operates using two distinct parallel branches. One focuses on global feature extraction, capturing the overall context of an image, while the other zeroes in on local feature details, isolating specific regions of interest. STN employs different metric measures for these features: the familiar Euclidean distance for global aspects and Kullback-Leibler divergence for local measurements. This dual approach allows the model to weigh the strengths of each feature type during classification without the complexity of additional adaptation modules. The result? A single streamlined framework that can efficiently process images and yield impressive accuracy in few-shot classifications. What makes this particularly interesting is that blending these complementary features can lead to enhanced performance across various tasks, not just image classification. For instance, if this principle can be applied to other domains like audio-visual data or even text, it may pave the way for multimodal AI systems that can learn from limited data in diverse contexts. The simplicity of the SAIN design, Combining these features, without resorting to heavy adaptation techniques, reinforces its potential applicability across a variety of use cases. However, while the CEN framework shows promise, it's essential to consider the implications of relying on pre-trained vision transformers for feature extraction. The performance of the CEN could be significantly impacted by the quality and diversity of the pre-training data. If the pre-trained model is based on a dataset that lacks variety or is not representative of the target domain, the CEN's effectiveness may be compromised. This concern raises questions about the model's robustness in real-world applications, where input data can vary widely. Additionally, the paper does not adequately address the computational complexity and efficiency of this proposed architecture. While the authors emphasize the dual-branch design that extracts both global and local features, they do not provide a detailed analysis of the computational demands associated with using the vision transformer in this context. The efficiency of this approach, in terms of training time and inference speed, is crucial for practical applications, especially in resource-constrained environments. Now that we've uncovered the innovative features of the CEN framework, it's time to dive into the broader implications of this research. We'll explore how these contributions not only affirm the importance of dual complementary feature extraction, but also forecast exciting possibilities for future AI applications. The CEN method addresses a long-standing hurdle in few-shot learning, namely, the difficulty of establishing reliable comparisons between images using either global or local features alone. This innovation draws inspiration from human cognition, revealing how our brains instinctively merge overarching patterns with intricate details to identify new objects. While this research adds a significant piece to the puzzle of evolving AI capabilities, it also invites a re-examination of how we approach AI model design more broadly. By recognizing the importance of using complementary features in tandem, researchers can pioneer new architectures beyond image classification, improving adaptability in emerging sectors such as medical imaging, autonomous vehicles, and even robotics. Moreover, the study suggests that optimizing distance metrics can open new avenues for AI research, setting the stage for models more aligned with real-world complexities. Imagine a future where machines can not only see and learn, but also interpret and understand contextually, resulting in AI that can make decisions based on a combination of features just as humans do. This connection opens the door for cross-disciplinary approaches that elevate performance without overly complicating model architectures. However, we must also consider the potential for overfitting that may arise from the meta-learning approach employed during the training phase. While the authors assert that their strategy effectively harnesses the potential of both global and local features, the risk of overfitting, particularly when trained on a limited number of tasks, is a significant concern. The paper does not adequately address how it mitigates this risk, leaving a gap in understanding the model's true generalization capabilities. Given that few-shot learning tasks hinge on the ability to generalize from minimal examples, this aspect is critical. The attention maps visualized through CEN provide compelling evidence for the notion that visual categorization systems can effectively learn where to focus their processing efforts, similar to human cognition. This realization not only validates the potential for further advancements in few-shot learning, but also invites inquiries into how such attention mechanisms can be translated into other contexts, such as automated surveillance systems or medical imaging. These fields could benefit from enhanced focus on critical features, much like the CEN does with its attention maps in image classification tasks. The successful demonstration of CEN across multiple benchmarks suggests that insights gained from its design could be applied to other machine learning domains. For instance, the concept of integrating disparate feature types to enhance performance can inspire developments in fields like natural language processing, NLP, and speech recognition, where hybrid representations could lead to better understanding and classification of nuanced data. This realization directs attention to exploring alternative ways to more dynamically integrate such measurements within real-time applications. The CEN framework breaks new ground in few-shot image classification, rethinking how we leverage features in AI models. As we navigate this rapidly evolving landscape, The research reveals that simple architectures can deliver substantial performance improvements, dispelling the myth that complexity equates to capability. The implications are profound. In an age where data is abundant, yet challenging to interpret, methodologies like SAIEN will become essential in making AI both efficient and effective across a wide range of applications. However, addressing the limitations associated with pre-trained models, computational overhead, and the risk of overfitting will be crucial for ensuring the robustness and practicality of the SAIEN framework in real-world scenarios. This study does not merely provide a solution. It encourages future exploration into hybrid approaches that could ultimately expand the horizons of machine learning. So, could the Siamese Transformer Network become the gold standard for few-shot learning? Only time will tell, but one thing is clear. The doors to innovation are wide open. Thank you for tuning in. If you're intrigued by the advancements in deep learning and AI, be sure to like, subscribe, and hit that notification bell for more insights into the future of technology.